All right, this is the test review, the first test review for area and volume, and in the current packet that we're in, it's page 16 in your packet. If it's a different year, it might be a different page. I'm basically going to walk through the setup of these because I have provided the detailed worked out answers for you, but I'm going to provide a little bit of support, and then we'll take a look at the answers to see how to work the problems completely out. So problem number one, you have two functions, f and g, and f is a square root function, which is given right here. It's already graphed for you in green, so this is f of x. And then you have the equation of a line, 6 minus x, which is this line right here. And those two curves form a region whose name is R. So R is this region right here, the enclosure. It's also bounded by the x-axis, and it's shown in the graph to the left. We see a point of intersection where f and g intersect at 4, 2. We see a point of intersection at 6, 0, and we know that there's a point of intersection at 0, 0 if we need that. So for letter A, we're finding the area of region R in terms of x. So we know if we're finding the area of a region, we're going to integrate, if we're in terms of x, top minus bottom dx. There is no pi because we're not doing volume, we're doing area. And this one says set it up and then evaluate by hand. Now, remember when we learned this, we talked about standing in the room and looking up and seeing the ceiling and floor. But if you move to two different parts of the room, the ceiling and floor differ at different points within the room. So in this particular case, we're going to have to write two integrals, one for this region over here from 0 to 4, and the top curve is the square root of x, and the bottom is the x. And then a second integral for, we're going to add that to the integral from 4 to 6 because the top curve changes in that particular region. So when you set that up, what you're going to see, as you can see from my work right here, and my line, I don't know why my line moved. I can't get it to move back. This dotted line that you see should actually be right here. I did an enlargement of the graph and it didn't enlarge, it didn't grab the line correctly. So we are accumulating the area from 0 to 4 under square root of x dx. We're going to add it to the area from 4 to 6 under the line, which is 6 minus x. I'm not going to explain the antidifferentiation. It's pretty straightforward. I antidifferentiate separately, do the arithmetic, and you should get 22 over 3. The note that the area is bound by two different functions, so it has to be accumulated under each function independently and then added. So I did talk about that. All right, let's go back to the second problem. So in 1b, we are finding the area of the same region, but now we are going to be in terms of y. Now, we have a little bit different situation going on in terms of y, because if you're standing in the room and you look to the right, you're going to see the line, and if you look to the left, you're going to see the square root function. So you're going to see the curve. So this line stays on the right all of the time. The curve stays on the left all of the time. So we're in terms of y, so we're going to accumulate from a low y value to a high y value. We're going to do the right curve minus the left curve dy. So we're going to have to change the g of x, which is y equal to 6 minus x. We're going to have to get x by itself. So x would be, subtract the 6 and divide by -1. That'll give you 6 minus y. And then we're going to have to get y equals square root of x. We're going to have to get x by itself, square both sides, and x is equal to y squared. So the right curve will be 6 minus y. The left curve is y squared. And remember, we're finding area, not volume, so there is no pi. So when you look at the answers, here's my right curve, here's my left curve. So I have the right curve, which is the line, minus the left curve, which is the square root function, but in terms of y. The low y value is 0, and the high y value is 2. And then you can drop the parentheses and put it in descending order, do the power rule anti-differentiation, substitute, and evaluate. The area is being calculated in terms of y, so it's a right curve minus the left curve. I want to reset this thing because there we go. My vertical line, all these vertical lines that I created have moved. So let's just reset that and make it look better. All right, let's go back to letter C. We're using the same region. So for C, we're going to simply set up. Oh, by the way, letter B was evaluate with your calculator. Make sure you're reading the directions carefully. Letter C, set up an integral to find the volume. So now we're moving to volume of the solid formed by revolving region R around the x-axis. Now remember, we're still going to have that split where the curve, when we revolve around the x-axis, the radius from the axis of revolution to the curve in this region is going to be top minus bottom, and the axis of revolution from to the curve, top minus bottom. So even with this volume problem, we're going to have to set up two integrals, one for this region right here, and then a separate integral for this region right here, but we are finding volume. So we're going to have our pi. We're going to accumulate from 0 to 4, we're in terms of x, and we're going to have the square root of x squared as the radius for that one. And then we're going to set up a totally different or separate volume with another pi. I mean, I guess you could keep that out front and put brackets or parentheses or something. From 4 to 6 of 6 minus x, quantity squared dx. So we're back to finding volume. We have pi r squared. Letter C says do not evaluate, so that's your answer for that. Letter D, set up an integral to find the volume of the solid region R revolved around the line x equal to 6. So if I put in the line x equal to 6, which is right here, this puts the problem in terms of y. So when I find, and there's clearly going to be a hole, that region is not flush to the axis, so little r of y is going to be the right curve minus left curve, and big R of y is going to be from the axis of revolution to the outer curve, right minus left. We are in terms of y, we're finding volume, so we're going to need a little r of y and a big R of y. Little r of y is 6, right side, minus parentheses, the line in terms of y, so that was 6 minus y. And then we're going to need big R, which is the right side of 6, minus the left side in terms of y. And then you're supposed to evaluate that with your calculator. So let's look at the answers over here. So for letter, that was C, I think, yeah. And in letter D, let me reset that because my lines moved all over the place. So you can see exactly what I said before. Big R minus little r. You can distribute or combine your like terms there, distribute the negative and combine your like terms, and then you can type this into your calculator and get the decimal answer. All right, let's reset this. All right, so that's, all right, now we're on to number 2. We're using the same graph, but we are using the graph to answer some questions. So carefully read. Suppose that h of x is a function that indicates Mr. Jernigan's velocity when he is running, where h is a piecewise function comprised from f and g from above. So we have our same graph and our same functions. H of x is measured in velocity, or excuse me, is measured in meters per second. So this is a velocity graph. I want to remember what I'm looking at. Letter E says, set up an expression that could be used to determine Mr. Jernigan's average value of velocity from 2 to 5 seconds. So when I look at 2 to 5 seconds, here's 2. I'm just going to kind of block it off from here. And, oh no, look what's happening right smack dab, well, not in the middle, but in between the 2 and 5. The changing of the curves is happening again, so I'm going to need 2 average value integrals. So I'm going to need 2 integrals, let me say that. Now we're going from 2 to 5, so it's going to be 1 over b minus a, so that would be 5 minus 2, so it's going to be 1/3 is going to be my overall divider. I'm dividing everything by 1/3, but then on the inside I'm going to have 2 separate integrals. So I'm going to accumulate now from 2 to 4, because that's the breaking value, and we're going to do the area under the square root of x dx. That takes care of the first region. Then we're going to add that from the integral from 4 to 5 under, I forgot what the equation was. What is it? Back up at the top. 6 minus x dx. So notice that I did not do 1/2 of this integral and 1 of this integral. The average is to divide the entire integral by the span, so that's 1 over b minus a. So we're only setting up what units is the average velocity measured in, what it is the average of the velocity. So the velocity is measured in meters per second, so that's what this is going to be measured in, meters per second. And you are not evaluating, and you can see on my answers for number 2, where are the answers? Here we go. These are in your packet, by the way. And so this is exactly what I was talking about. Same answer. Just trying to walk through them and give you some explanation of what's going on in case the detailed notes are not enough. All right, so for letter E, we're okay, that noise in the background is my dog Gypsy playing with one of her toys, so it's okay. Set up an expression that could be used to determine Mr. Jernigan's average rate of change of velocity. So pay attention to these two phrases. Average rate of change of velocity is not the same as average value of velocity. Average rate of change is slope of velocity. So we're literally using the slope formula on the velocity function from 2 to 5. So that's simply going to be v of 5 minus v of 2 over 5 minus 2. So now to find v of 5, I'm going to substitute 5 into the equation of the line. To find v of 2, I'm going to substitute 2 into the square root function. Now let's talk about units. V in the numerator is already measured in meters per second. The denominator of time is measured in seconds, so that's meters per second, which is meters per second squared for letter F. Set up an expression that could be used. So this would be the expression. It does not say that you have to evaluate it, I don't think. And what are the units? We have meters per second squared. All right, moving on to letter G. Oh no, we're interpreting a derivative. So remember, h of x is the name of the function in general, and h of x indicates Mr. Jernigan's velocity when he is running. Hopefully it's fast. So find h prime of 5 and interpret the meaning in the context of the problem. A derivative modifies what? Its preceding function. So h prime, in this case, will modify h. So the subject of my sentence is h. So I ask myself, well, what is h? H is Mr. J's velocity when he runs. So the subject of my sentence is Mr. Jernigan's velocity. That is what is going to increase or decrease. All right, now h prime of 5, so here's 5 right here on my graph. H prime, this is the graph of h, so you have to kind of go slowly through this. So if this is the graph of h prime of 5 is the slope at 5. Now notice that 5 is on a line segment that is decreasing, therefore the slope is negative. So I know that h prime of 5 is less than 0. Now not only can I tell you that h prime of 5 is less than 0, I can tell you what it is because it's on a line segment. So I'm going to fall 2 units and run to the right 1 unit. So, nope, sorry, run to the right to get back to the line. Come on, Jernigan, you can do better than that. So fall 2 units, run to the right 2 units. That would be -4 over 4. So h prime of 5 specifically is -1. So let's look at our sentence that we're going to be here for letter, I forgot what it was, but we'll figure it out when we see it on the answer sheet. Back here. So at 5 seconds, the subject of my sentence, Mr. Jernigan's velocity, you could add in when he is running, is decreasing at a rate of 1 meter per second squared because, point off for me, h prime of 5 is less than 0. All right, going to 1h. For 1h, assume, view browsers, assume the graph is valid. Let me clear the screen and give myself a little more paper here. All right, assume that the given graph is valid for 0 to 6.5. So 6.5 we'll say is about right there. Is Mr. Jernigan speeding up or slowing down at 6.2? Now remember, to determine if a particle, in this case if Mr. Jernigan is speeding up or slowing down, we need to know the sign of velocity at 6.2 and we need to know the sign of acceleration at 6.2. Now remember, the given graph up here is velocity graph, so at 6.2, we are past 6, the velocity is clearly negative because the graph is below the x-axis, so velocity is negative, and since the velocity graph is decreasing, the acceleration or the slope of velocity is also negative. Since velocity and acceleration have the same sign, Mr. Jernigan is speeding up, which is what I would expect him to do, of course. So for letter H, we are, Mr. Jernigan is speeding up because velocity is less than 0, acceleration is less than 0, and notice my clear explanation. Since velocity and acceleration have the same sign, Mr. Jernigan, was speeding up. That's letter H. Letter I, we have another contextual problem. In the context of the problem, interpret h of x. So remember, h of x was velocity. So we are accumulating the area under the velocity curve, and so if we integrate velocity, we're going to get back to position. The big question is this representing displacement, or is this representing the total distance Mr. Jernigan traveled? And so we need to make that decision, we need to know the sign of velocity. So I'm going to come back up here and look at my graph from 1 to 4. And so I can see the graph from 1 to 4. All of the area is positive. Therefore, I could say that the definite integral represents the displacement. Mr. Jernigan traverses, I guess I would say, from 1 second to 4 seconds. I could say the total distance traveled by Mr. Jernigan, and both of those would be, or I could say change in position, all of those would be totally correct. Have no idea what I wrote on the answer sheet, so let's see. The definite integral represents change in position. So right here where it says change in position, you could also have in this case, you could say the displacement measured in meters. You could say the total distance traveled measured in meters, because all of the area is positive. And that's what I said right there. Let's go to number 2. Number 2, we have another piecewise function, and the piecewise function begins at -2 pi and stops at 4 pi. The graph is given, and the name of this function is g of t. Oh, yay! The derivative of a definite integral. The derivative of a with variable, no, we have a constant lower bound, so that's good. Variable upper bound. There are 3 steps. Step number 1, take your integrand and take out the t. That's what take out the t looks like. Step number 2, put in the new function, and this is the new function right here. So I'm going to substitute. You could write pi x or x pi, it doesn't matter. I'm going to write pi x down here. That's put in the new function. In step 3, we're going to multiply by the derivative of the new function, which is simply pi. All right, now we're supposed to calculate that at x equal to 3. So g of, I'm substituting 3 in place of x. So 3 pi times pi. So g of 3 pi, so this is 1 pi, 2 pi, 3 pi is right here. All right, now I need to know the y value at this given x value so I can multiply it by pi. So this is 3 pi. Now what we see here is the equation of a line. So I'm going to write the equation of that line so I can figure out the y value. So y minus y1 is equal to m times x minus x1. The point that I'm going to choose, because I try to be smart lazy, is this point right here at 0, 2 pi. I like to use zeros. I could have used 4 pi, 0, doesn't really matter. But I'm going to use the y-intercept, 0, 2 pi. So y minus 2 pi is equal to, I don't know yet, x minus 0. Now the slope is going to be a fall. So I'm going to go down 2 pi, so that's negative 2 pi, and to the right 4 pi. Pi's are going to divide out. That's going to give me negative 1/2. So the slope is negative 1/2. So y is equal to negative 1/2 x plus 2 pi. So I got y by itself, and I need to know g of 3 pi. So y is equal to negative 1/2 times 3 pi plus 2 pi. So that's going to be negative 3 pi over 2 plus 4 pi over 2. I'm just getting a common denominator. 2 pi is 4 pi over 2, which simplifies to be pi over 2. So g of 3 pi is pi over 2 times pi, which is pi squared over 2. So that is the derivative at 3. All right, and then, let's see, I don't want to erase this in case I need it. If big G, so that's the antiderivative of little g, big G of negative 2 pi equal 4, and G prime, big G prime is G of x, find G of 2 pi. All right, so this is a given condition. So I am beginning with 4 units of area already calculated. We've seen these before. So I have 4 units of area. I'm going to add to that starting, remember this is my starting value, starting bound, negative 2 pi. I want to go to my stop of 2 pi. And I'm going to accumulate the area under g of x dx. So let me erase some of the markings that I have on my diagram over here. There we go. And I'll get all that stuff out of my way. All right, so I have 4 units of area already accumulated, so there's my 4, plus the bounds are in order, so we're going to go from negative 2 pi, so I see the area of a triangle, so that is 2 pi by 2 pi, which is 4 pi squared, divided by 2 is 2 pi squared. I don't trust myself doing arithmetic in my head. So 2 pi squared times 2 pi squared is 4 pi squared, and half of 4 pi squared is 2 pi squared. Okay. And then the area of the other triangle is going to be 4 pi by 2 pi. 4 times 2 is 8 pi squared. Half of 8 is 4, so that's going to be 4 pi squared. So that's going to be 4 plus 6 pi squared. All right, let's see if I agree with myself on these 2 last ones. So number 2, yep, pi squared over 2, and for number letter B, I said 5 pi squared. Interesting. 4 plus 5 pi squared versus what did I get? 4 plus 6 pi squared. I agree with this. I think it's 4 plus 6 pi squared. I think I have an error. I don't think I made any calculation errors. So 4 plus 6 pi squared. Good thing I took a look at that. And that's review number 1.